So these are some standard series that we can get directly from the Taylor series formula because they're easy to differentiate. The exponential function, all right, standard. You can get this radius of convergence. The easiest way to get it is from the ratio test, but you can also do it from the root test. It's just a little bit awkward to do the kth root of k factorial. All right, it's a little bit awkward. Sine and cosine, same expansions from single variable calculus. Notice that they have the same radius of convergence of infinity, implying that they converge in the entire complex plane. These three functions are entire. They're not polynomials, so that means that all three of them must grow in at least some directions as the modulus of z grows without bound, faster than any fixed power of z. Okay? Because recall, if anything grows in a manner that's bounded by some fixed power of z and it's entire, then it must be a polynomial. All right? By integrating the geometric series, we'll get an expansion for the capital logarithm. I prefer to write it this way, minus log 1 minus z. If I put the minus signs over here, then I don't have to worry about any minus signs over here. Notice that the form is very similar to that seen for the exponential function. But the missing factorials lead us to a strikingly different radius of convergence. This series converges on the disk modulus z less than 1. It converges everywhere on its circle of convergence except at z equals 1, where of course it diverges as the harmonic series. We have one additional series that we can get from our Taylor formula, and that is the binomial series. All right, I'm again going to center this series at 0. All right, and we can just repeatedly take derivatives. And so on and so forth. All right, so thinking carefully about that and plugging in the value at z equals 0, you should see that this gives us all right, that expansion. Taking a cue from the well-known binomial series expansion, we can rewrite this like that. All right? Where n choose k has this explicit form. But what it actually represents is you just start with the top number and then you subtract 1 repeatedly until you have the bottom number of terms in the numerator of the fraction. The denominator of the fraction is always the bottom number factorial. All right? We can find the radius of convergence of this expansion by using the ratio test again, just because it's the easiest test to use. All right? What we find is that we're taking the limit as k goes to infinity of this. Well, as k goes to infinity, this just goes to 1. So this expansion also has a radius of convergence of 1. This has, of course, exactly the same form as the binomial expansion has, but n does not have to be a natural number. It doesn't have to be an integer. It doesn't even have to be real. Okay? So as an example, real quickly, one, two, 3 terms, so I'm done. All right? 1/2 choose 3 is equal to 1 over 16. It loses all of its combinatorial meaning, but it still represents an effective coefficient in this expansion. All right, so those are the standard expansions you want to be aware of.